Hi everybody. Hope everybody's having a good day today so far. And today we are going to talk about quadratic forms. Now quadratic forms are going to be really important for enabling us to determine whether a function is concave or convex, and in fact actually quasi-concave, quasi-convex, and quadratic forms are going to be very important for us to determine whether we have a maximum or a minimum of a function, whether we're optimizing. It'll give us necessary and sufficient conditions to tell us when we have a maximum or we have a minimum, for example, of a utility function, a profit function, cost function, and so on. So let's get started here. Let's start off by looking at a typical second-degree polynomial, a typical quadratic function. So let's say we're looking at a quadratic function, a second-degree polynomial function, and we're going to do this first on R, so real function. So the function, let's say f of x is just a real number because we're on R. F of x, let's say, is, well, we typically write polynomials, or one way we write them is like this. And of course, if we have a higher degree polynomial, third degree, nth degree, we would keep having more terms, a3x cubed and so on, as we've seen already. But we're just going to be focusing on these second degree polynomials. And in fact, what I'm going to do is I'm going to instead of having these subscripts, because I'm going to need subscripts or something else, and it could get a little messy or complicated, I'm going to instead write something else for the coefficients. Let's write this as c plus bx plus ax squared. And I'm going to write this also as capital C of x plus capital L of x plus capital Q of x, where C of x is the function that is always just the number C, the constant. So that says this is a constant function. That's the first term. L of x is the second term, b times x, which is linear. That's for the L. And Q of x is the quadratic term here. So let me write that down over here. Let's say C of x is equal to C for every x. And L of x is equal to bx. And Q of x is equal to a x squared. So this again is the constant term. This is the, I'll call it the pure linear term. Well, it's the linear term. Okay, it's the linear term. You don't need pure for that. And this is the quadratic term. The reason I put the pure in here in parentheses is because of what I want to write over here. So I've said constant term. It's a function, so it's the constant function. This is the linear, the pure linear function, not affine. So it's homogeneous. It's the pure linear function. That's the second term. And this is the pure quadratic function, which is the third term. So let me just write function in here. And that's the reason for putting the pure in here. If I'm talking about it being just the linear term or the quadratic term, I usually don't put the pure in here, and people wouldn't do that. Let's just note, we're going to be focusing just on the quadratic term. We're going to be ignoring these terms. We can analyze those terms separately, and we actually have analyzed, of course there's nothing to analyze here. Here we have analyzed pure linear functions on vector spaces. So here we're going to be today just focused on the quadratic term alone, and we'll just ignore this stuff here. So we'll just focus on functions like this, which look pretty simple, right? So let's add here that the derivative of the quadratic term function is 2ax, and the second derivative of the quadratic term function is 2a. Now, let's draw a little picture of each of these. So let's say that, let's first look at the case where a is positive, so that the second derivative is 2a, which is positive, and that's something that we kind of already know how that works. That's going to look like this. This is the, let's say, the y-axis, the vertical axis in the target space. And the horizontal axis, of course, goes right here because, note, one of the characteristics of this quadratic term is that when x is 0, the quadratic term function is 0, whatever a is, positive, negative, or itself 0. So this is the function q of x here, and this is the case a greater than 0. It's true that, let me just right here on the side, for all x, in fact, let me say this is for all x other than 0. So for all x except 0, I have q of x positive, strictly positive in this picture because a is a positive number. And notice that the quadratic term function q of x is a convex function. Then I'll draw the corresponding picture over here for the case a negative. Here, the graph of the function is entirely below the horizontal axis. So this is q of x. This is the case a negative. This is the case where for every x except 0, we have qx negative, and it's a concave function. And in fact, strictly convex, strictly concave. So let's even put that over here and here, because we might as well note that in each case it's strictly convex, strictly concave. And then we have one remaining case, and that is a equals 0. If a equals 0, the second derivative is 0. Actually, the first derivative is 0. And so if a is 0, the q of x function is just 0 everywhere. So that would look like this. Here's x. Here's y. And let's just say that this is q of x. It's everywhere 0. And so here we have the case a equals 0. For all x not 0, q of x is 0. And of course, in this case, it's 0 for x equals 0 too. And it is a constant function. It's both convex and concave, but it's not strictly convex or strictly concave, of course. Right? So that's the picture. That's a complete story, really, for pure quadratic functions that have no linear term and no constant term. When I say no linear term and no constant term, what I mean is that this is 0 and this is 0, so we can drop those out. So f of x is just this, or q of x. So if we're interested, as we're going to be today, in analyzing the quadratic term, the pure quadratic functions, the ones on R, the real functions, they are simple. Complete story is right here. A is positive, A is negative, or A is 0. That's what things look like. Now, of course, how quickly it goes up, how quickly it goes down, depends on how big A is, how big negatively A is. That's the whole story. That's everything. Okay, now, if that's all we wanted to do, there wouldn't be much to do. But the trick here is, what we really want to do is we want to figure out what happens for quadratic functions on Rn, on domains of dimension larger than 1. So let's first see what we get for R2. Let's see what the pure quadratic function that has only quadratic terms in it, and of course here there's only just the one term. Let's see what it looks like when we have the domain as R2. So here you can see that we've written out, again, q of x, but now x is x1, x2, is two components because we're in R2. And notice that instead of just that one term here, and in fact, let's focus. I keep pointing up here, but that could be confusing because we could be having this in here. I'm focusing just on this, so let's just focus right here. So this will focus my attention a little better on just this function here for R1. So here in R2, instead of just the one term, we have 4 terms. We have all 4 quadratic, well, the quadratic term consists of all 4 of these terms in this sum, I guess, if you like, right? So we have a sum of 4 terms taken together. I would call that, and I guess most people would call that, the quadratic term in this kind of quadratic function. And so notice that every one of the terms has the x components appearing exactly twice. It's as if this was a times x instead of ax squared. This was written as axx. It would still be the same function, and that's the way this is looking up here. Here, the x appears twice in the multiplication because it's quadratic, that is, it's second degree. And here, instead of one term, there's 4 terms because there's 4 combinations of x1 times x1, x1 times x2, x2 times x1, and x2 times x2. And so we have the sum of those 4 terms, which, of course, we could write in matrix notation with a row vector, a matrix, a 2x2 matrix, and a column vector, carry out the matrix multiplication, and we would get a real number. We would get the real number that's up here. And notice that I've written that as just xax. And now you can say, but wait a minute. If x is a row vector, then the second x in the xax should be x transpose. Or if x is a column vector, then it's the first vector that should be transposed. And that's correct. But I'm actually here not thinking of x as row or column vectors. I'm just thinking of them as vectors. So I'm going to use the notation xax without putting transpose on it to always mean that if you want to carry that out as a matrix multiplication, then the first x is a row vector and the second x is a column vector. But another way to think about it is that xax is just a shorthand notation for this sum up here of 4 terms. Okay, so that is the quadratic term in the polynomial we would have here on the domain R2. And we can figure out the constant and the linear terms, but today we're just interested in the quadratic term. So now let's actually see what happens if we are in R3. So in R3, you can see here we have q of x, but x has three components, x1, x2, x3. And so same thing as for R2. There we have 2 times 2 equals 4 terms in the sum. Down here we have the sum where I goes from 1 to 3, sum where j goes from 1 to 3. And so when we take that double sum, we have, of course, 3 times 3, or 9 terms. And again, we can write it out as a matrix multiplication. And again, I'm writing it as x, a, x, where now the x's are 3 vectors, 3-dimensional vectors, and the A is a 3 by 3 matrix. And of course, you can do the same thing for R4. You would get I equals 1 to 4 twice, and you'd have 16 terms, and I don't want to write all that out. You'd have a 4 by 4 matrix with a 4-dimensional vector on each side, and so on. For any n, you're going to end up with, in fact, let's write that down here. You can see here that I've done the same thing here for n as I just did for 3. So the quadratic function as function of x1 out to xn, double sum from I equals 1 to n, sum j equals 1 to n, aij times xi times xj, xi times xj. In every term, we have the components of the vector x1 to xn. We have the components appearing twice, 2 appearances of a component. And of course, sometimes it's the same component when I equals j. And so, of course, we have n squared, or n times n terms, and xax is an n. We have an n by n matrix, and each of the x's is an n-dimensional vector. So that's what the quadratic term will always look like. So now let's actually, before moving on, let's see a picture. We have these pictures here of everything that could happen when n is 1. When we have a quadratic function in R, as I said before, this is pretty simple. We can see everything right here. Let's take n equals 2. So we're back in the case here where n equals 2, and let's actually draw a picture of what the quadratic form might look like in that case. So here we first have the quadratic form that is an analog of this, but with a 2-dimensional domain, so our picture's in 3 dimensions. So this is the analog of this, a strictly convex function. So it's the analog of a positive, but the problem is there's not just one number a here. We have to deal with 4 different coefficients. So it's not obvious what we could say would be the relation between the 4 coefficients and the graph looking strictly convex. Here it was easy. Graph strictly convex when the a is positive. So here we have the situation where whatever those coefficients have to be to get there, where the graph is strictly concave. And here we have the corresponding picture, corresponds to this, for n equals 2 domain, where the graph is strictly concave. I think I might have said strictly concave over here. Strictly convex here. So strictly concave. And so you might think that like this, the graph's always going to be either strictly convex or strictly concave like this, or a constant. Just 0. It would have to be 0. As you can see, at 0, the 0 vector, this is always going to be 0. So it would have to be, if it's constant, it would have to be 0. But that's not the case, because here's a third picture when n is 2 of a quadratic form. And this is the graph of a quadratic form here that, as you can see, is not concave, not strictly concave or convex. It's not even concave or convex, right? Some directions it's concave, other directions it's convex. But that's a quadratic form, and we'll figure out what the A's would be to make the quadratic form look like this, or like this, or like this. In particular, we're going to actually do an example where we work out some of the details of this quadratic form down here. Okay, so now let's take this off because I want to say a few things about, a few more things about the general quadratic form over here. So we'll take this off now. Okay, so here on this side of the screen, we are going to look at a couple of details connected to these quadratic forms. So let's notice that in the quadratic form on R2, the one with just two variables and four terms, notice that the terms A11, the terms with the coefficients, A11 and A22, the ones where I've got x1 times x1 or x1 squared, x2 times x2 or x2 squared, there's only one of each of those terms. One A11 term, x1 x1 term, one A22 or x2 x2 term. But then notice that when I've got A12 and A21, if you like, down here, when I is unequal to j, I have kind of twin terms. One for ij. Suppose I is 1 and j is 2. I've got one for ij, 1, 2, and one for ji, 2, 1. So I've got these kind of twin terms up here. And of course, I've got x1 times x2 and x2 times x1, which are the same thing. So actually, notice that the sum of those twin terms in this, even not just in the R2 case, but in the Rn case, the sum of those twin terms is going to be ij times xi times xj plus aj times xj xi. But because xi xj is the same as xj xi, that is the same thing as aij plus aji times xi xj, or xj xi. It doesn't matter what order I write these in. In fact, I could, if I like, gather together these twin terms and write them as each one of them is one term, or each pair of them is one term. We could do that, and we sometimes do that. In fact, I will do that at one point shortly. But for the most part, we actually keep them separate. But notice, too, that if we write let's say aij tilde equals aji tilde equals 1/2 aij plus aji. And so let's go over, at least in the R2 case, we can actually see the actual terms. So you can see that here we're saying this is going to be the sum of the two off-diagonal terms in the matrix, right? And so I've said, let's take those two off-diagonal terms, which don't have to be the same as one another. Of course, they could be different. Those A12 and A21 could be different coefficients. Let's take those two potentially different off-diagonal terms in the 2 by 2 matrix. And in fact, let's just rename, let's substitute in, instead of those two potentially unequal off-diagonal terms, we'll substitute in these new numbers, which are the same as one another, and each one is 1/2 of the original sum of the two. And so now these two are the same. And we do this, in fact, both of these, you'll notice, these are true for every ij pair. This is true, and this is true. And so if we write this, and then name the new matrix, instead of naming it A, naming it A tilde, because it has these as terms, then A tilde is a symmetric matrix, because a symmetric matrix is defined simply to be exactly a matrix in which the off-diagonal terms that match up are equal to one another, right? So then A tilde is a symmetric matrix, but also for every x in Rn, because we're doing this in Rn, these are vectors are in Rn, it's the case that x A tilde x is the same as x ax, because we haven't changed the sum. We haven't changed the sum, so that means that using the A tilde matrix, which is symmetric, or using the original matrix, which perhaps isn't symmetric, we get the same value for every x. So our q of x, if this is q of x, then this is also q of x, the same function, right? So we can change around the coefficients without, in a certain way, without changing the function. And when we have the function represented by the symmetric matrix, which would be unique for the function, no matter what these coefficients are, I can always turn them uniquely into the average of the two. So for any quadratic, pure quadratic function like this, it can be represented uniquely by a symmetric matrix. And so while we define this as a quadratic function, whatever the a's are, when we have the symmetric form of the function with a symmetric matrix, we refer to that as a quadratic form. So quadratic form is really just a quadratic function, like either of the two situations here. It's just a quadratic function, but it's a quadratic function where we represent the function by its symmetric coefficient matrix. So as it says here, quadratic form on Rn is just a function on Rn, a real valued function, which has the form xax, where A is a symmetric matrix. So this is what we've said at the outset today that our lecture would be about, would be these quadratic forms. Well, we finally got at least to saying what a quadratic form is. And so now we're going to go forward and actually study quadratic forms and their properties. And so I'm going to take this off, and we'll use this space to talk about a number of the properties of quadratic forms.